So let me talk you through the elements of this slide here. So up at the top left corner, we have this standardized grid of color chips, and different languages around the world carve up this color grid differently into named categories. So if we look at Wobe, language from the Ivory Coast, that language is said to have 3 basic color terms. So here they are in the table here, and you've got rough glosses on the right here. So roughly speaking, a term for white, a term for dark, and a term in the red yellow region. And I'm going to be showing you a number of these little plots here. And the way to read these pictures is that all of the regions in the same color, those are regions where the same term is used by speakers of a language. So Wobe speakers, all of the regions that an English speaker might call purple or pink or red in the grid here, those are referred to with this form saying by a Wobe speaker. We see different kinds of maps for different languages. So this map here from Buglere is showing that there are more basic color terms in that language. And here's a list of them on the right here. And so looking at these maps is a good way to get a bird's eye view of what the categories are in a color naming system, how many of them there are, and where the boundaries between them might lie. Okay, so second example of thinking about organizing experience into named categories is tense. How do people think about time? What category systems do we have for coding time? So a simple way to get at this is to imagine a timeline running from the past to the future. And for today, I'm going to work with a relatively simple course timeline, which has just 7 elements. So we've got the present in the middle here. We've got 3 pasts, remote, near, and immediate, and 3 futures as well. And so just as for color, different languages around the world carve up this underlying space differently into categories. So the English tense system has 3 categories. We put the 3 pasts together into a past tense. We've got a present tense and a future tense. For Zulu, the situation's a bit more complex. So on the right here, I'm showing you part of a table from a book by Nurse on tense and aspect in Bantu languages. And I've taken just the column from this table that's about perfective aspect. And you can see he's suggesting here that there are these 2 pasts in Zulu, 2 futures as well. And for the purposes of the analyses I'll be showing you later, this is how we carved up the timeline to capture what he has in that book there about Zulu. Okay, so one way to think about one of the really fundamental issues here is captured by this quote here, which Nick Evans has at the start of his chapter on semantic typology. This quote here from David Lewis, which talks about carving things at the joints. So one of the fundamental questions of semantic typology is what are the natural ways to carve reality into categories, and how does understanding that give us some insight into how different languages around the world carve up reality into perception of reality into categories? As John already mentioned, there is an idea in the linguistics literature going back a long way that linguistic systems are shaped by 2 competing forces. And these forces have different names in different parts of the literature. And I'm showing just 3 examples here. So early on, there's the idea that there's this tensional opposition between a drive for clarity or a drive for comfort. In optimality theory, the 2 basic principles are referred to faithfulness and unmarkedness. And Horn's formulation of pragmatics, he refers to the Q principle and the R principle. So as far as I can see, what all of these formulations share is that there's one principle which refers to the idea that language should be informative. It should allow the recipient of a message to understand precisely what was intended. So that's the drive for clarity. The drive for comfort is the idea that it's good for messages to be brief and easy for the speaker to generate, and easy for the recipient to process as well. So these opposing ideas. There's an interesting paper on communicative efficiency from 2002 by Rilke, and he includes this table mentioning a number of different theoretical approaches from the literature. I believe it's correct to say that in all of these cases, you can see in one way or another the opposition between these two basic principles. So I picked out just a couple of examples for the left of the slide, but if you dig into the literature, these ideas run through all of these parts of the literature. Okay, and competing motivations is often the slogan that's used for this idea of the competition between these two forces. I'm going to talk a little today about how we can use information theory to formalize this same basic trade-off and apply this formal theory to applications, including color naming and tense. So to give you an idea of how this might work for color, John showed a picture like this already, where we put the two fundamental dimensions on the X and Y axis of a plot like this. And I'm going to be showing you a number of pictures where we have a gray region of the plot. So that's the part which is impossible for any system to achieve. The white region of the plot is the region where possible systems lie. And there's going to be this optimal frontier, which is the place where we have systems that are achieving a near optimal trade-off between the two dimensions. So to give you a rough sense of this, if we look at this plot here, think about what a system at the origin might look like. This is a system which has very, very low complexity and very, very low communication cost. And so communication cost is something like a measure of how much difficulty the listener has in reconstructing what the speaker intended. So a system right at the origin here, well, that's easy. Well, that would be something like mind reading. This would be a system where the speaker does very little, generates a very, very brief form, and then somehow mysteriously the listener manages to know exactly what the speaker had in mind. So mind reading, something like that is not really achievable. This system up here is achievable. In the case of color, this would be a case where you have a single label for all of the different chips in that grid. So that's very, very low in complexity because there's just this single label, but it incurs a high communication cost because when a speaker utters this single label, a recipient isn't going to really be sure what's intended. The other extreme would be to have a different label for every single different chip in the grid. So that would be a system that's very, very high in complexity, but communication cost is minimal because the recipient can know exactly what the speaker had in mind. Then somewhere in between, we have systems that achieve near optimal trade-off between these dimensions and are more manageable in complexity while incurring relatively low communication costs. So in between is going to be the sweet spot for actual attested linguistic systems. Okay, so here is a picture from Shannon's early paper that really laid the groundwork of the branch of information theory called rate distortion theory. So I'm going to use this acronym RDT throughout today. And I'm not going to talk you through exactly what the symbols on this picture mean and exactly what he had in mind here. The high level point for now is just that Shannon was talking about the same kind of trade-off that I just informally introduced for color naming. And it turns out that the theoretical apparatus he introduced in this paper can be used to formalize the trade-off between communication cost and complexity and to apply these ideas to linguistic systems. So as the outline for today, I'm first going to talk about a model of communication that's called lossy communication, because this is a place where rate distortion theory applies and is useful. I'm then going to take color naming as the main example that we work through. We'll then turn to tense systems, and I'll do that in a bit less detail, and then finally give you a very, very quick list of other places where rate distortion theory has been applied in linguistics. So here's a picture of communication across a channel that John already introduced, and I'm showing an example here involving numerals. So imagine speaker is looking at a single pebble, say, and wants to convey that quantity. Speaker generates the form 1. Let's assume that this is a noiseless channel, so the recipient can pick up that message without any error or distortion. And this is lossless communication. So receiving that message allows the recipient to know exactly what the speaker had in mind. Here's another example. So 11 pebbles, the speaker is going to say 11, and again, the recipient is going to be able to reconstruct exactly what the speaker had in mind there. Okay, here would be an example where we're thinking about lossy communication rather than lossless communication. So imagine that the speaker is looking at a dress which has this color and the speaker says blue. Well, this is lossy communication because the meaning reconstructed by the recipient is not going to be identical to what the speaker actually had in mind. So maybe the speaker's going to, maybe the recipient is going to think that it's a lighter blue than the actual color of the dress itself. Okay, so if you put lossless communication on this side of the slide and lossy on the other slide here, big difference is that for lossy communication, we're going to use the same form for multiple items. So multiple items get grouped together under a single category with a single category label. So this immediately raises the question which applies for lossy communication, but not lossless communication. The question of, well, which items get grouped together into the same category? So this is going to be the main question that we focus on today, but there are other interesting questions, and information theory has a bit to say about these questions too. So questions like, well, which forms are assigned to which categories? And these apply to both lossless communication and lossy communication. So the Zipfian idea that shorter forms get applied to more common concepts, that's relevant to both lossless and lossy communication. But for this part, let's focus on the question of which items get grouped together into the same category. Okay, so here's a picture of the simple communicative scenario that we're going to use to formalize these ideas. So imagine that the speaker over here has a brief glimpse of an object, say a dress, and the lighting conditions aren't that great. And so the speaker here isn't exactly sure what hue the dress might be. And so this probability distribution captures her beliefs. So she thinks it's most likely that the color of the dress falls within this part, sort of the darkish blue part of the spectrum, but she's got a bit of uncertainty here, and that's what this curve here or probability distribution captures. Now a speaker generates signal word W to convey this distribution that she has in her head. And then the listener receives this word and tries to reconstruct the speaker's distribution S. And so this is what the listener does. And you can see that the distribution is a bit broader and a bit fatter, and the listener is assigning some probability, for example, to the idea that it's a lighter blue than the blue that the speaker actually saw. Okay, so with this communicative scenario in mind, we can start to think about formalizing the two dimensions in the plot that I showed you before. So the dimension here on the y-axis, we're going to call it communication cost and formulate it in terms of the discrepancy or the distance between the speaker's distribution here and the listener's distribution. So if those distributions were identical, communication cost would be 0 and we'd be down here on the axis. If they're not quite the same, we're going to be higher up along the axis. And the precise way we do that is using the KL divergence, which is an information, you could think of it very roughly as an information theoretic measure of the distance or the discrepancy between two distributions. So that's our formulation of the principle of informativeness or clarity. It has this clean formulation in terms of information theory. That's right, as John says, KL is Kullback-Leibler divergence. We're going to formulate the x-axis here in terms of an information theoretic concept called mutual information. And John is going to give you a definition of this in the next part. For now, let me just say we're going to think about the mutual information between the distribution in the speaker's head and the word W. And so you could think of this as the amount of information in bits that the word provides about the distribution in the speaker's head. So in a case like this, where there's a single label for every color chip, Well, hearing that label actually gives you no information at all about the distribution in the speaker's head. So this is very, very low complexity. In a case where the label pins down the hue quite precisely, that's going to be a case where the word W is conveying lots of bits, and so complexity is going to be high. So the actual definition here is in terms of number of bits conveyed by the word about the speaker distribution. But as a good first approximation, you could think of complexity for today as number of categories in the system, and you won't go too far wrong. Okay, so in a few slides, I'm going to show you results where we actually analyze real color naming systems in terms of this framework, but there's sort of a little niggling detail I need to mention first, which is that I'm going to take these plots from a paper by Noga Zaslavsky, and she has, unfortunately for us, flipped the y-axis. So instead of the communication cost measure I just introduced, she's just flipped it. So now the simplest possible system is down here. But otherwise, these plots are the same. There's the gray unachievable region, the white achievable region, and the optimal frontier, along which we find systems that achieve optimal trade-offs between the two dimensions. Okay, so let's talk about the basic elements we need to actually apply these ideas and these definitions of communication cost and complexity. So actually, the most important part of the whole framework is how we formalize the idea of the distribution that the speaker has in her head. And for the little picture I showed you before, to make things easy for the diagrams, I was showing color as a one-dimensional spectrum, and we were thinking about a distribution over that one-dimensional spectrum. For the model results that I'll show you in a few slides, we're actually going to use this three-dimensional representation of color space. So this three-dimensional color space, it's a bit like HSV, hue saturation value space, if you know that. The one we actually use is called CLAB. And the reason for using that space is that it is based on psychological data, sort of psychophysical experiments. And this CLAB space has the property that distances in the space roughly correspond to psychological distances, to perceptual distances based on the human visual system. So here's CLAB space, and instead of this distribution over the one-dimensional space, we're going to think of a distribution in this three-dimensional space. So as an example of this, imagine this little probability cloud centered in the blue region such that more probability is assigned to the interior of this sphere, and then the probability tails off towards the edges. So something like that is the speaker distribution. It's critical. What's actually doing most of the work for the model results I'll show you in a minute is that this color space is lumpy. If the color space were perfectly smooth, so think of something like a billiard ball, then there would be no joints that we could talk about, carving reality at. But the fact that the color space is lumpy means that with the help of information theory, we can begin to think about, okay, what are the natural ways to carve this lumpy color space at the joints? So you'll notice, for example, that there's this lump in the yellow region. And as a consequence of that, you'll see in a little while, the rate distortion theory model, color naming I'm going to show you, is inclined to introduce a yellow category relatively early on in the piece to kind of carve this lumpy yellow part at its joints. Okay, so the second element we need is the prior distribution. And for color naming, this gets cashed out as a distribution over all of the color chips in the grid here, which captures something like the probability that speakers will need to talk about those different hues. So what I'm showing you here is a prior distribution based on corpus statistics in English. So look at the relative frequencies of red, yellow, and so on, and use those to construct a prior distribution. For the results, I'll show you in a bit, it's actually a different prior, but it turns out that the prior doesn't matter hugely for the qualitative results I'll show you. What's much more important is the structure of color space.
Charles, there's a question from Alice you might take.
Yeah, I see that. I'll take that in a moment when we get back to those trade-off plots.
Sure.
Okay, so it's important that we're going to use the same prior for all of the languages. So we're going to assume this prior is based on English statistics. We're going to assume that that's universal. That's just an easy place to start. You can relax that assumption and work with the idea of culture-specific priors, and there's now some work which makes that step. So let's now talk about the data that we're going to use here. So these are data drawn from the World Color Survey. And so this is a data set that includes a little more than 100 languages from around the world. And in each case, the linguists and anthropologists involved collected naming data from on the order of 20 or 30 speakers. So this would be an experiment where for a given speaker, you go through the entire grid in some random order, say, and you ask the person to provide their name for each color chip here in the grid. And so I'm showing you here these little maps that I mentioned before for 3 of the languages in the data set. Also the map here for English, which is drawn from another data set. And the plots at the top here are based on showing the most common term for each color chip. The plots at the bottom here are for the same language, but they capture some of the uncertainty. So the white regions are regions of color space where speakers don't agree. There's no color term that gets chosen, say, more than 40% of the time. So these plots here are useful for capturing the fact that color naming is sort of soft and probabilistic. Okay, so we have these data for about, let's say, 20 or 30 speakers per language, and you can average over those responses to get an estimate of this probability distribution, the probability that a speaker generates a particular word when looking at a particular color. Okay, so here is the 2-dimensional plot that I showed you before, and now I've added blue dots showing the 110 languages in the World Color Survey plus English, so 111 in all. And you can see that they're falling along the optimal frontier here. So they're not exactly on the frontier, but they're pretty close. And so the interpretation here, sort of the big take-home story, is that color systems look the way they do because they're achieving near optimal trade-offs between communicative cost and complexity. So this is a functional account of why color naming systems look the way that they do. Okay, so let me try to come back to the questions in the chat. First, Alice's. The grade region seems to suggest that she doesn't think lossless communication is possible. So yes, that's right. Well, so lossless, the fact that the fact that it looks like the optimal curve here flattens out, I think that's really an artifact of the fact that there are about 300 color chips there in the grid. If you really treated color as this continuous space that could be cut up infinitely finely, then I think that the curve would keep on going up. But really, in terms of what's out here, by the time you're thinking about hypothetical color systems with 300 different categories per chips, that 300 different color categories, that's far from what languages are actually like. So it's not maybe that relevant to actual languages. Which dot is English? I don't actually remember. It's in Nogga's paper. I think it's sort of it's not neither the most complex. So English has about 11 basic color categories. There's some languages have a few more than that. So English is towards the more complex end, but not the most complex. So maybe up here somewhere, but I forget exactly where. Alison asks about the geographical and linguistic distribution of the 110 languages. So Berlin and Kay and Cook set up, kind of deliberately tried to get data from a broad set of language families, and they were focusing on languages from cultures that were sort of relatively untouched by industrialization and these sorts of things. Okay. So putting these dots on the plot and seeing that they're near the optimal frontier, so that's somewhat interesting. But what's most striking to me is when you look at the actual optimal systems predicted by the theory and compare them to a tested system. So you see in many cases, the optimal systems look rather similar to a tested system. So I've picked out 3 examples here. Here's the color naming system for Kalina, and you can see it has these 4 categories: a light, a dark, a red, and a yellow sort of category. Here is the optimal system that matches Kalina for complexity. And you can see that it's not identical to the attested system, but the model is doing a pretty good job of predicting where the category boundaries should lie. I've got examples here for Agarabi and English, and you can see again, the model is not getting the category boundaries exactly right, but it's doing a fairly good job, at least what seems to me to be a pretty impressive job at predicting where the category boundaries are going to lie. So when we're thinking about these sorts of plots, I mentioned that the white space is the region of possible languages, and there's a lot of white space here for non-optimal languages. Well, what do they look like? So there are languages in there which I guess the maps here would look like sort of salt and pepper diagrams. They have disconnected regions of color space. So probably it's not surprising that, you know, actual attested languages don't look like that. But you can think about comparison classes that are maybe more feasible as possible hypothetical languages, and it turns out that those aren't optimal either. So one way to construct such a set of comparison languages is to take an attested system. So I'm showing you the naming diagram for Kalina, and you can think about rotating that. So think about taking this map here and then just shifting it to the left or right, and shifting it in a way that the categories wrap around when you get to the right or the left boundary on the plot. And so you can see here's what Kalina would look like if we shifted it to the right here. So this reddy category would turn into more of an orange category. And Noga went off and analyzed all of these rotated systems. And this plot here I'm showing you is based on data across the entire World Color Survey. On average, the actual attested systems, so those are at rotation 0, they're more efficient, they're more optimal than the rotated versions of the systems, suggesting that, you know, what's going on here is more than just the prediction that attested systems ought to be, attested color categories ought to be connected, because all of these rotated versions are connected too. The information theoretic model here is picking up on more than that. So the idea is it's somehow able to carve that lumpy color space at its joints in a way that goes beyond simply just generating connected regions. Okay, so Thomas has a question here. Is the way this model is predicting where the category boundaries will be connected to, there seems to be a correlation between the number of color categories and which ones they end up being. So yes, I think that's connected to the Berlin and Kay evolutionary sequence, which I'm going to talk about now. So if it's not, let me know and I'll come back to this later. So Berlin and Kay noticed from their initial data set in this area that there seemed to be this orderly sequence in which color terms were introduced. So some of the languages in their sample had only 2 basic color terms, one for light, one for dark. And then they noticed, well, if you look at the 3-term color systems, almost invariably, the 3rd category that it gets introduced is in the red region of color space. And then if you look at the systems that have 4 or 5, after red, the categories to get introduced are green and yellow and so on. So that's what this evolutionary sequence represents. And it turns out that Noga's rate distortion theory model captures this evolutionary sequence to some extent. So here are some examples of optimal systems along that optimal frontier. And you can see this one here is a system that has a light, a dark, a red category, and a yellow. This is a similar system that's now at a green as the next category after yellow, and so on. So if you look at the trajectory of optimal systems predicted by this information theoretic framework, it actually gets this early stage wrong. It predicts that yellow ought to come along before red. But after that point, and remember I pointed out to you before that lumpy color space has a big lump in the yellow region. So that's why the model likes yellow as the first category to come along after light and dark. So in that respect, it departs from the data, but after that, it does a decent job of capturing the order in which color terms enter the language. To give you a sense of this, here's a video that Nogga made. And so I'm going to show you what happens if we start here with the least complex system and sweep along the optimal frontier. And if you keep your eye on this part of the plot, you'll see the optimal systems at each part along that trajectory there. We're starting with the category with 1. Here's the yellow category coming in. Next is red. Now we see a green coming in. Blue category. Okay, and now we're out in the sort of implausible region here. So one of the interesting things about this sequence is that it captures, to some degree, not only the order in which categories emerge, but the fact that there's uncertainty in color naming. So you would have seen those white regions where the model is not very certain about the name. It's interesting that the model can pick those parts of the, can capture that aspect of color naming as well. So the question was, can I explain again why the model introduces yellow first instead of red? If we go back to the picture of C-Lab space, so this is the psychologically motivated color space we're using, and it has this big lump in the yellow region. And so if you think about like carving this lumpy thing at its joints, the first carve to make is to separate the yellow lump from everything else.
Charles, why is yellow the first? Is it because if you look at kind of the wavelength, like perceptually, it's easier for people to see, or like, I guess, why is yellow so lumpy there?
Yes, it comes down to how the human visual system works. So I think it's not possible to trace this down all the way to like how the cones, the color sensitive cells in the eye work, although Berlin and Kay made some suggestions along those lines early on. Turns out that sort of perception of color is hard to reduce exactly to photoreceptors. So it's something to do about the basic way in which the human visual system perceives color. So I guess that's an interesting thing that's maybe separate from the focus of this model because it's a non-linguistic. It's sort of a non-linguistic thing, and this theory of color naming is sort of a theory about how names get kind of built around or on top of that perceptual substrate. Okay, so there's a question about, would the model also depend on the distribution and salience of colors in the world? So yes, this is a prior part here, and that makes a difference and it's important, but I think it's less important than the lumpiness of the color space, because if you run the model where you use a uniform prior over the entire color space, the model performs a little bit worse, but it still makes sort of similar qualitative kinds of distinctions. Okay, so Alice is saying, well, why wouldn't we expect red to be lumpiest then, given that red is picked out first? And so this is something that's unresolved in my head. There's kind of a disconnect between the naming data, the fact that red comes out first in naming, and what C-Lab is telling us about color space. Okay, there's a question about prevalent symbolism of reds versus yellow. That's a really interesting topic, but I'm afraid it's not something that I know about. Okay, so let me sum up the message about a color naming system. So first point, color naming systems achieve near optimal trade-offs between communication cost and complexity. And second, this particular model, I think the two main things that it was able to do that are most striking to me is the fact that it accounts for color naming as a soft graded probabilistic sort of thing. Previous models in the literature weren't so good at that. Also, the fact that it helps to explain how color naming systems might emerge via a continuous trajectory. If you look back at the Berlin and Kay sequence, that's really just a sequence of discrete jumps. And it's a little bit mysterious just based on this sequence, how a new category would get introduced. The video that I showed you at least helped me to think about how you could get from one of these stages to another in terms of a smooth, continuous trajectory that a language might more plausibly follow. Okay, so since we're at 10:30, I'm not going to say too much about tense marking. Let me just say that you can apply the same sort of idea where instead of having a speaker conveying a distribution over color space, now we have a speaker conveying a distribution over the timeline. So I think what I'll do is I'll just show you the main result plot here. So this is a result where we're looking at 10 systems from a database of on the order of 100 or so languages. English belongs to this big dot here. So this dot here is for languages which have one category for past, one for present, and one for future. The size of the dots here represents frequency in the data set. And so you can see, again, most of the attested systems, but not all, are lying close to the optimal frontier. And in this case, there are some interesting things to say about the languages like this one. I think this is Hiskariana, and why they're away from the optimal frontier and why that might happen. So this is really just to give you a taste of this, and I'll point you to Frank's paper for anyone who's interested in reading about the details here. Okay, let me also show you these two plots to just give you a sense of, this is now kind of zooming out and taking a more bird's eye view of the literature. What are the places where people have looked at this trade-off between communication cost and complexity using information theoretic ideas? So Frank's paper on tense also includes analyses of grammatical number and evidentiality. Nogger and collaborator have a recent paper on personal pronouns, and all three of the results on this slide are using exactly the same information theoretic framework, the rate distortion framework that I presented to you today. There are related analyses in other parts of the literature that are again looking at two dimensions, and these two dimensions almost always capture the same high-level ideas, but the formulation is slightly different. So in particular, the way in which complexity gets formulated varies across these different projects, but there are applications to kin naming, numerals, quantifiers, and indefinite pronouns. Okay, so let me finish this part by doing two things. So first of all, talking about what I see as an important open question. So there's some evidence that for color naming and some other domains, languages are achieving near efficient trade-offs between these dimensions, but there's a big questions about how languages got that way. The video I showed you in the Berlin and case sequence suggests a historical sequence where maybe languages moving from simple to complex progressed along the optimal frontier, something like this. But it's also possible that languages started off further away from the optimal frontier, then over time, these systems became more efficient as they were repeatedly used by speakers. And I think diachronic studies are really needed to try to untangle these different possibilities. I point you to some of the limitations and criticisms of this work that looks at trade-offs between two dimensions. And I think the best paper along these lines is by Levshina. So she mentions a couple of concerns she has about this work, and I'm going to mention two here. So first, she says it's difficult to identify the exact nature of the costs and benefits. So if you're thinking about complexity, for example, what exactly is complexity and why does it matter? Is complexity an issue because complex systems are hard for children to learn? Is complexity an issue because complex systems make it hard for the speaker to retrieve the relevant information? There are sort of lots of possible causal reasons why something like complexity might be relevant, and you kind of need to understand in more detail exactly what that factor is before being sure you have a good explanatory theory. A second important point he raises is that looking at binary trade-offs is a problem if there are other relevant costs and benefits. So I focused here on communicative cost and complexity, and it could be that learnability is a third axis, a third dimension that's relevant. And so it might be that if you're looking at only two among the multiple dimensions that are relevant, you get a slightly distorted picture of what's going on. Okay, there's some interesting comments here in the chat about cultural salience and so on. From an information theoretic perspective, there's a recent paper coming out of Ted Gibson's lab that talks about these issues. So I guess for people interested in the intersection between information theory and cultural salience, that's a good place to look. Okay, pragmatic reason is another application of rate distortion theory. I just wanted to mention that and give you a pointer to the reference for anyone who's interested. And let me now turn to the overall conclusions. So in addition to the same kind of conclusions I already mentioned for color and naming, let me just say that a similar sort of theoretical framework can be used to analyze tense marking and other kinds of grammatical marking. And I didn't talk about this so much today, but one of the valuable things about information theory is that it gives you a unified way to think about both form and meaning in a single framework. So here are the two recommended readings that I suggest as entry points to the literature. And I'm a little over time, I think, so I'll stay around for a bit, but why don't we break as a group? And I think we'll be coming back at 11 o'clock. Is that right, John?
11 o'clock indeed. Thanks, Charles. That was great. I feel like I understand especially the color study much better now. So many of us will want to take a break until 11. I will go and take a break to refuel. Perhaps if some of you have further questions for Charles, he said he might be here for a few more minutes now. And what I will do, I will actually then come back in a few minutes I'll be back here before 11. If people have some more stuff they want to discuss before I kick off again.